Hello everyone, thanks for watching this video. Today I'm going to talk about our work LDL, which aims to stably generate perceptually realistic details while inhibiting visual artifacts in GAN-based SISR tasks. GAN-based SISR methods have recently attracted significant attention for its potentials to recover sharp images with rich details. However, adversarial training is unstable and often introduces unpleasant visual artifacts. Therefore, how to inhibit the visual artifacts of GAN-SR without affecting the realistic details becomes a key issue. To tackle this, we investigate in depth the GAN-SR methods and categorize their results into three typical types of regions as shown in this slide. Specifically, Type A patches like the flat sky or long edges are easy to reconstruct since they are smooth or contain only large-scale structures. In contrast, it is difficult to produce high-fidelity SISR results for patches of Type B and Type C because they have many fine-scale details and suffer from signal aliasing in the degradation process, where most high-frequency components are lost. Fortunately, for texture like Type B patches like animal fur or tree leaves in distance, the pixels are randomly distributed so that the differences between SR results and ground truth are insensitive to human perception. Therefore, rich details generated by SR methods can lead to better perceptual quality in these regions. However, patches of Type C like thin twigs and dense windows in the building contain many fine-scale regular structures or sharp transitions among adjacent pixels. The distorted structures and overshoot pixels generated by GAN-SR methods can be easily perceived by observers as unpleasant artifacts. Since SISR is an ill-posed task, one LR input corresponds to many possible HR counterparts scattering in the high-dimensional image space. As shown in this figure, the adversarial loss can update a blurry solution along with many possible directions, some yielding perceptually pleasant results and some producing unpleasant ones. This leads to an unstable optimization process that may generate artifacts along with details. According to the above investigations, we should inhibit the generation of artifacts in Type C patches while preserving the realistic details in Type A and B patches. To achieve this challenging goal, we carefully design a pixel-wise map to discriminate artifacts from realistic details, as well as a learning strategy to stabilize the training of GAN-SR models. We first calculate the residual between the ground truth image and the SISR result to extract high-frequency components. Then, based on the observation that artifacts usually consist of overshoot pixel values, we propose to calculate the local variance of the residual map as the primary map to indicate artifact pixels. Since some pixels in patches A and B will also have a large response, the local variance may cause wrong punishment on the generation of realistic details. To address this issue, we further calculate a stable patch level variance from the whole residual map. To avoid over-penalizing the realistic details, we then stabilize the training process and refine the artifact map. Specifically, we use the exponential moving average technique to temporally ensemble a more stable model which usually has few artifacts. At locations where the residuals of the optimizing model are smaller than that of the stable model, the model is updated in the correct direction and should not be penalized. We see that the locations of fine textures and desirable edges are removed from the refined artifact map so that the penalty can be imposed more precisely on the artifact pixels. The overall pipeline is shown here. Given the refined artifact map M-refine, we calculate an artifact discrimination loss during training. We validate the effectiveness of the proposed LDL method on top of 3 representative backbone networks with a scaling factor of 4 following prior arts. This table compares quantitatively the state-of-the-art GAN-SR methods and our LDL. We can see that our proposed LDL scheme improves both the perceptual quality, LPIPS, DISTS, FID, and reconstruction accuracy, PSNR, SSIM, on most benchmarks under all 3 backbones. This figure presents some visual comparisons among the GAN-SR methods using the RRDB backbone. Similar conclusions to the quantitative comparisons can be drawn. LDL generates much fewer visual artifacts, especially in regions with fine-scale aliasing structures. In addition, by regularizing the adversarial training process, LDL is able to reconstruct more details with high fidelity, such as the areas with regular patterns. We also apply the LDL to the real-world SISR task. As can be seen in the area of dense windows, our LDL suppresses the generation of artifacts and encourages sharp details. In the area of twigs, the proposed LDL improves the generation of fine details, benefiting from the explicit and accurate discrimination between artifacts and realistic details. For more analysis, please refer to our paper. Thanks for listening. Our codes and pre-trained models are available on our GitHub. Feel free to contact me if you have any questions.